Let's flip this around, keeping the light fixed and showing the effect on the sphere. In fact, throughout this unit, let's assume each light is extremely far away, like the sun, so we can just look at its direction instead of its position. That way, we don't have to think about the light's direction changing as the surface changes position. Here the sphere's normal changes with respect to the light. The light's effect is at a maximum at the top of the sphere, goes to 0 at the equator, and stays that way since the bottom of the sphere faces away from the light. This is what the diffuse term looks like when the sphere is lit from above. This next point is a little subtle, but I think it's worth going through. A diffuse material is defined as one that scatters light in all directions above the plane according to this cosine law. So this green shows how the amount of light scattered actually drops off as the angle gets steeper. That is, the amount of light from a single point on a surface drops off with the cosine of the angle of the surface compared to the eye. So you might think less light would hit the eye when the surface is viewed from a shallow angle. However, a balancing factor is that as the angle of the surface to the viewer increases, the area of the surface visible through the pixel proportionally increases. That is, you see more of the surface even though less light per unit area is reflected towards the eye. These offsetting effects give the net result we want. The viewer's location doesn't matter at all, as the shade of the surface depends only on the angle to the light itself. Not needing the eye direction makes the diffuse term faster to compute, which is always important in interactive rendering.